Wednesday, May the 3rd, 2023. Reading Albert Einstein's Out of My Later Years has been a very fulfilling experience because it's one of the only real treatises I know by the man himself that is, as of after his career and global career, and then after he went to the Institute for Advanced Study, and after his walks with Gödel and all that kind of stuff, or what it might have been, where it was said that both of those men, where Einstein was a touchstone of the times for foundations in physics and Gödel was a touchstone of the times for the foundations of logic, that they both ended up being visitors at the Institute for Advanced Study on the East Coast of the United States and in the United States. That it worked out that they became friends somehow, it's said, or apocryphally it's so. And so they would take walks and, discuss things. And so it's interesting to think that Einstein might have derived some of his notions on the theoretical from Gödel, and Gödel some of his notions on the theoretical from Einstein, and vice versa. Maybe it's so. So where we had left off in this reading was right after the Riemannian curvature and the gravitational field equations with Riemannian metric or pseudometric, and then a reduction of the whole mechanics of gravitation to the solution of a single system of covariant PDEs. Theory avoids all internal discrepancies which we have charged against the basis of classical mechanics. To say avoid doesn't mean resolve, it just means to be agnostic of, in a sense, or insofar as that Einstein's statement and position about classical mechanics is a thing. There's kind of a question about velocity. Velocity, meters per second or seconds per meter. It's about the same. Meaning that though in the changes in one, make quantity as grow or shrink, kind of the opposite way. It's the inverse, the reciprocal. But the units of the acceleration, is meters per second, and then how would that be when it was seconds per meter per meter? You can see that it's reflecting whether it's changes in the velocity in space or changes of velocity in time. There's some question about how and when it gets to regard that as a natural unit. That it makes for systems of these complementary duals, why it's relevant that it's a thing. Velocity or inverse velocity? Which one is in terms of time? How is it so in either way? This is an interesting kind of thing that we'll see some later development. It is back to Einstein. It is sufficient, as far as we know, for the representation of the observed facts of celestial mechanics. But it is similar to a building, one wing of which is made of fine marble, left part of the equation, but the other wing of which is built of low-grade wood, right side of equation. The phenomenological representation of matter is in fact only a crude substitute for representation which would correspond to all known properties of matter. There is no difficulty in connecting Maxwell's theory of the electromagnetic field with the theory of the gravitational field, so long as one restricts himself to space, free of pondable matter and free of electric density. This is where we discussed about that electromagnetic waves go through the electric field, whereas light goes through space that's pretty much otherwise empty. And here, free of ponderable matter and free of electric density. All that is necessary is to put on the right side of the above equation for TIK, the energy tensor of the electromagnetic field in empty space, and to associate with the so modified system of equations the Maxwell field equation for empty space, written in general covariant form. Under these conditions, there will exist between all these equations a sufficient number of the differential identities to guarantee their consistency. These are usually matters of continuity and or symmetries and conservation, but continuity laws here is the usual milieu of things. Expressing anything that can be written as a conservation law with a symmetry can be written as a continuity law. And it's not necessarily so that things that can be written with a continuity law can so be written as symmetry in a conservation law. That they're transitions and they represent limits and infinitary processes to arrive at crossing boundaries, which in the linear is still just a straight line defined by what it crosses. Under these conditions, there will exist a sufficient number. We may add that this necessary formal property of the total system of equations leaves arbitrary the choice of the sign of the member T sub ik, a fact which was later shown to be important. This in the sense that it's a magnitude only and signless or directionless, which otherwise may have been added up from either way. There's been talk here about arithmetic and deconstructing arithmetic to make sure that there's ways that things that would be modeling numbers can build up as if they're additive in that regularity, and they can be modeled as if they're built up by division of wholes and that regularity, and that they happen to add up when it's infinite, the whole thing, in Euclidean and a lattice, that they happen to result in the same things, but that otherwise is not necessarily so. Whether or not there exists a standard model of the integers, or that there's only fragments or non-standard extensions, is maybe a fact in number theory, and it explains how there can be conjectures and when there are theories with a point and infinity and the theories without. And if so, what are the behavior of prime numbers and roots at these constants 0 and infinity? It varies. There are many systems that model them that have that they are consistently kind of like so or various. That there's not a standard model could mean that there are many different means to so attain to it. And this is the kind of thing that is about the mathematics and the foundations of mathematics, which result the usual, most fundamental and elementary number systems. TIK, the energy tensor of the matter, is left signless, even though it's only represented as negative TIK in the field equation. In terms of the scalar of Riemannian curvature, the gravitational field tensors, field equations, and the curvature. And the curvature tensor. The desire to have, for the foundations of the theory, the greatest possible unity has resulted in several attempts to include the gravitational field and the electromagnetic field in one formal but homogeneous picture. Here we must mention particularly the five-dimensional theory of Kaluza and Klein. Having considered this possibility very carefully, I feel that it is more desirable to accept the lack of internal uniformity of the original theory, because I do not consider that the totality of the hypothetical base of the five-dimensional theory contains less of an arbitrary nature than does the original theory. It's fair to say that Kaluza and Klein just kind of have a projection. The fifth dimension of Kaluza and Klein is just a freedom for whatever moves out and about. It's basically a fourth dimension for a fourth dimension that wasn't really originally existent. That if everything's parameterized by t somehow, and it's the space that has these changes about the metric, that every object in its space has its metric, and this kind of thing. He's saying that it's probably not fruitful to go out in all these higher dimensions to do so, but when it's usual enough that in these higher dimensions, just to get to that, the atomistic is expressed again in what's doubled that, the superstring theory. It's again about the models in the mathematics and geometry, of course, that the non-standard geometry in any shape of thing is very much forbidden. and considered outre because it's entirely unavailable to the senses, as it were. The same statement may be made for the projective variety of the theory, which has been elaborated with great care, in particular by Danzig and by Pauli. The foregoing considerations concern exclusively the theory of the field, free of matter. And he says matter, but it's to include anything that the electrical field, if they're electrons, those are particles in the electric field. How are we to proceed from this point in order to obtain a complete theory of atomically constructed matter? In such a theory, singularities must certainly be excluded, since without such exclusion, the differential equations do not completely determine the total field. Now, there are advances into mathematics like the meromorphic and these means of establishing what was nonlinear to be linear again, or to build it so this way, and the models and the approximations and the inexact, that Einstein is really kind of took a stand that he wants to see a total time parameterized or differential equation modeling the whole thing. And so then the singularities represent several kinds of issues. So one thing is that there's singularities in the gravitational singularities. And so it's to be said that there's definitely kind of existence evidence, or that according to experimental modeling by Chandrasekhar, after Schwarzschild's radius of a region which would be so dense in its mass that it would affect gravitational strength so great that it would result that it would only grow without otherwise being disturbed by changes in the relativistic frames about it that would disrupt its core and at the one moment just somehow making a space warp or wobble that spread it out enough that it would instantly dissipate. That otherwise, that's one kind of singularity. And the other kinds of singularity are singular forms of equations. I mean, gimbal lock is bad enough, which is basically when you have a gyroscope and multiple axes that there's a contrived way to spin it around so that it would, instead of floating freely and that the gyroscopic action kept it rotating in one orientation, that the gimbals would lever on their action moments all the way around. And so when you could spin that around in a contrived manner, and it would break otherwise the behavior of the rotating frame to keep its orientation in space, that it has this rotational inertia, it's an inertial system. And there are other singular surfaces to consider, and again, these represent usually asymptotes. And so then in the nonlinear and the highly nonlinear, these are things that present particular challenges to computation and modeling. And then there's the very fact that if there's a spiral space-filling curve at an origin, that's also a sort of singularity. For singularity theory, mostly people only have the asymptote, which is where a function goes to infinity. As the domain of a function, a continuous function, goes to a finite number, that the range, the value of the function so evaluated, goes to infinity. Asymptote. That is asymptotic. That it doesn't have a symptote, which is as related, I imagine, to the tangent. The spiral space-filling curve is also this kind of thing. And so it represents kind of a backdrop for that. And it's also funny because the spiral space-filling curve is its own antiderivative. So anything to do with the differential, and what's the property of the differential? Well, it's its own antiderivative, the exponential. So according to the theory of differential operators, you can treat the exponential very specially because there's a family of identities. Then is whether that's unique or whether that's distinct, because, well, at least some other function is its own antiderivative, is a very special thing. It's a special function. The foregoing considerations. How are we to proceed? In such a theory, singularities must certainly be excluded, since without such exclusion, the differential equations do not completely determine the total field. Here, in the field theory of general relativity, we meet the same problem of a theoretical field representation of matter as was met originally in connection with the pure Maxwell theory about singularities. And so there's things like, well, there are no magnetic monopoles. It's like a gimbal lock. It would lead to solutions that would not be so. And it kind of gets into these kinds of notions of singularity theory, where in the singularity, it's just kind of like that it's either a hole or a vacuum in the middle instead of a giant spike or something like that. That there are non-standard functions that belie their finite inputs. These are just some of the kinds of concerns which make it so that a mathematics that has such things may find that whatever you can actually model in mathematics can have a physical model and an interpretation that's proper. But there are also ones that would have nonsensical applications, and that they are to be excluded, except in so far as what results modeling them contains enough context that it's not nonsensical. So Einstein, with some of these more available tools in analysis, in the nonlinear analysis, in the singularity theory, in the geometry, and in the non-standard analysis, maybe then when he would express his desiderata about the total field theory, about this more concretely, eventually say, yes, I mean in terms of time. I mean universally parameterized by time, for example. Or yes, I mean in terms of conservation symmetry, or in terms of this restitution and dissipation, these tendencies and propensities. That would be so. That would be fair. Here again, the attempt to construct particles out of field theory leads apparently to singularities. Here also the endeavor has been made to overcome this defect by the introduction of new field variables and by elaborating and extending the system of field equations. Recently, however, I discovered in collaboration with Dr. Rosen that the above-mentioned simplest combination in the field equations, gravitation and electricity, produces centrally symmetrical solutions which can be represented as free of singularity. Well-known centrally symmetrical solutions of Schwarzschild for the pure gravitational field, and those of Reisner for the electric field, with the consideration of its gravitational action. We shall refer to this shortly in the paragraph next but one. In this way, it seems possible to get for matter and its interactions a pure field theory, free of additional hypotheses, one moreover whose test by submission to facts of experience does not result in difficulties other than purely mathematical ones, which difficulties, however, are very serious. Now, I'm curious if I didn't pick up that this was kind of already read a bit, relativity theory and corpuscles. No, this is kind of where we're at. I'd read ahead a little bit earlier, and so this was a quote that I had looked at before. And when we talk about this centrally symmetrical, like for Schwarzschild and Chandrasekhar, and then, well, outside the black hole, we got Kerr coordinates, K-E-R, or Kerr coordinates, or Kruskali's coordinates, and then inside is Schwarzschild, or Chandrasekhar, basically. And these centrally symmetrical solutions are basically examples of the meromorphic or free as of analysis about these kinds of things, which establish an inside and an outside. And just like there's the discussion of, well, I just have a Riemannian metric and a curvature tensor over there for anything that's a gravity well, and everything just goes straight around it. And it's entirely different regime in a sense, disconnected. It doesn't address how that there's a boundary and where exactly the boundary is and how the boundary is crossed and exactly what happens when it is. Of course, models over time have built up in us after that, then about stationary black holes and rotating black holes and how those are different. And supermodels of ultimately rotating black holes and these kinds of things. Then, for as was discussed earlier in these kind of talks, when there are just these kinds of singularities everywhere, the origin is anywhere, and there's white holes everywhere, and a Dirac positronic sea of virtual positrons and antipositrons constantly in an effervescence of auto-annihilation that never adds up to anything but zero, whether that's the empty space-time frame or not. Section 5, Quantum Theory and the Fundamentals of Physics. So quantum theory is taking a discretization. The whole idea of atomism is that, by definition, there's the smallest particle and it's a point. Surfaces and the materials don't necessarily admit that. Anything is granular, it's frangible. It's like they say you can fold a piece of paper in half, and you can fold it over itself again in half, and so on again, altogether in half. But that fold will grow around the singularity of the fold, that by the time you reach to the seventh or seven folds, that it can't be folded anymore. It's just not frangible anymore. It's not fungible. Now I've tried this, and it is possible. I'm like, well, yeah, here I have a piece of paper. I have folded it 8 times, but it eventually results in deformation. And so it's similar with the idea that there's a point in a particle. The whole idea of particle mechanics and the atomic model in electron physics, and we've discovered and found the mass of one electron, is a way to describe the objects of the theory, that then the behavior of these quantum particles, which is as well established that, well, it's a particle and it's a wave, it's particle-like and wave-like, helps establish that unnecessary attachments to the model result weaknesses in the theory, and that then the whole quantum theory is not a weakness in the theory, but a strength in the theory, because it's not leaving out the properties that are like true for these particles that are waves. And that here also that are waves of waves, and that are resonances in the extra local, those being Einstein's bodies and rigid bodies also. For the kinetics and kinematics as above the vibrations in thermal kinetics with respect to heat and optical and heat and the thermonuclear. The theoretical physicists of our generation are expecting the erection of a new theoretical basis for physics, which would make use of fundamental concepts greatly different from those of the field theory considered up to now. So far the field theory just expresses forces in the field, whereas in the field theory that, as was talked about yesterday or the previous time about the fields, is with the field occupation numbers, and all the fields have to live on one space-time frame. There's only one space-time for everybody. It's called the universe. It's by definition a thing. And I'm not going to get into multiple worlds interpretation because I consider it unscientific. Because after Copenhagen, which is like particles observe the behavior of objects as per statistics is fair, but then also that when we close one eye of the dual slit, that it always goes through the other one, but when we leave it back open, it goes through both. It really does. It really is by its operation mechanically like so. That I would accept, or a real Bohm to Broglie real wave function collapse for Schroedinger picture, not every time anything happens the universe splits, because it would just run out of resources. That would violate the principle of least action. It's unscientific because it would escape the realm of observability and all this kind of stuff. Now, that's not to say you can't model simulations of reality, abstract concepts of things, very, very high order simulations of things. For example, in a large numerical array maintained by a computing apparatus of the high parallelism and high performance. In that sense, the multiple worlds is just hypotheses. And then otherwise, there's that most peoples that have taken that out that the notion that there's no extra locality, there was no non-locality in the theories, and so they spooked themselves into a theory where it must be both at once, because empirically it is so. So these days there's a gentle retrenchment to Bohm and de Broglie is really visionary, and that these super classical models of the non-local exist, and it's going to be okay. So for Einstein, he says new sorts of methods of consideration. I'm curious what that's going to be here. While the failure of classical mechanics as revealed by the theory of relativity is connected with the finite speed of light, its avoidance of being infinity, it's not infinity, it's finite. It was discovered at the beginning of our century that there were other kinds of inconsistencies between deductions from mechanics and experimental facts, which inconsistencies are connected with the finite magnitude, the avoidance of being zero, of Planck's constant h. Here, this is that Einstein's cosmological constant is in a flat space-time universe, no different from an infinitesimal. Even that then is positive is just kind of effect that there is gravity. And it measures the entirely weak force of gravity everywhere, but being so omnipresent just adds up in all bodies of matter. So Planck's constant not being finite, meaning it's vanishing, is not unusual these days. It's called running constants, just like atomism vanishes. Every few years, science comes forward and says, here are the fundamental physical constants. And it's not that they add extra decimal points at the end. It reduces. They're called running constants. And so according to the energy and configuration of experiment, it's natural that it's an analog theory, and then that the trans-Planckian regime is just underneath the angstrom regime, in a sense, about the optical and the behavior of atomic nuclei, and atoms. It's similar with electron physics. It's like Millikan is like, I have measured the value of electron's mass, and 120 some years later, smaller. In a bigger experiment, but if you do Millikan's experiment, it's still the same. But if you put it up in one of these new $1 billion super colliders, it's not. So Einstein says, which inconsistencies are connected with a finite magnitude, the avoidance of being zero, of Planck's constant h. In particular, while molecular mechanics requires that both heat content and monochromatic radiation density of solid bodies should decrease in proportion to the decreasing absolute temperature, experience has shown that they decrease much more rapidly than the absolute temperature. For a theoretical explanation of this behavior, it was necessary to assume that the energy of a mechanical system cannot assume any sort of value, but only certain discrete values whose mathematical expressions were always dependent upon Planck's constant h. Moreover, this conception was essential for the theory of the atom, Bohr's theory, and it's correct. I mean, these numbers add back up. There are regimes about, as he's talking about thermo first and second law, and Rayleigh jeans, and the ultraviolet catastrophe, and these reasons why we have finite numbers for things, so that students, first of all, so that students can work up the derivations and know ways to work up the derivations through these things. And then later they can learn that these are the empirical things that go along with them, and then some explanation of the adiabatic and non-adiabatic why, and why not. And then there's, for this non-standard mathematics, is that otherwise you need to equip mathematics with sufficient continuum mechanics about infinitesimals and infinity. That the whole idea is that if physics should go forward without infinity or infinitesimals, because they suffer the vagaries of interpretation unless they are so well defined and figured out that our calculators cannot handle them, that the physics should go out that way. There's a point where it's vanishing, that possibility, but non-zero. for the transitions of these states into one another, and here that was framed in terms of the continuity laws, with or without emission or absorption of radiation, no causal laws could be given, but only statistical ones. And a similar conclusion holds for the radioactive decomposition of atoms, which decomposition was carefully investigated about the same time. For more than 2 decades, physicists tried vainly to find a uniform interpretation of this quantum character of systems and phenomena. And these days, it's still much the same. What happened when it worked out that they were looking for the extra local in something different than the Copenhagen interpretation, which is after Bohr and these great physicists, that it's got a stochastic probabilistic interpretation, as they went back to the competing theories and picked that up. Kind of like with Newton, and it's like, well, hey, for Newton, once we're trying to look for these competing theories, like what's the theory of gravity? And Einstein's just like, I just have a field tensors and they're in my space-time. It's called relativity. There's no force called gravity. These are just these models for it, and they happen to look like Newton's. Then there's that the Fadio and Lesage had their idea of a push gravity, that the outside universe kind of pushes things together instead of that they are pulled together. And then that's the same kind of idea as going back to Bohm to Broglie, where then Fadio and Lesage are basically put down because their models don't add up to that. It's not a classical theory. That the idea then is for this real wave function is being put up as a classical theory. But it's for the path integral, as has been read about, and then it does eventually involve some kind of superclassical notions of the gas, basically, and the models of gas for the models of fluids, that a gas is a superfluid. Yet it still embodies, for example, trades of pressure for temperature, or lack thereof, this kind of thing. So anyways, going back to Einstein, and he's declaring that all these different fields observe quantum mechanics, but the models are becoming contrived and cumbersome and weak and open to vagaries of interpretation, and it's a challenge. For more than 2 decades, physicists tried vainly to find a uniform interpretation of this quantum character of systems and phenomena. Such an attempt was successful about 10 years ago through the agency of 2 entirely different theoretical methods of attack. We owe one of these to Heisenberg and Dirac, and the other to Broglie and Schroedinger. The mathematical equivalence of the 2 methods was soon recognized by Schroedinger. So this is particle and wave. I shall try here to sketch the line of thought of de Broglie and Schroedinger, which lies closer to the physicist's method of thinking, and shall accompany the description with certain general considerations. Now, when I hear de Broglie, and about de Broglie and the electron also, I associate Bohm with the real wave interpretation. The question is first, how can one assign a discrete succession of energy value h sub sigma to a system specified in the sense of classical mechanics? The energy function is a given function of the coordinates q sub r and the corresponding moment p sub r. Planck's constant h reflects the frequency h sub sigma over h to the energy values h sub sigma. It is therefore sufficient to give the system a succession of discrete frequency values. These days in the non-linear and these ideas about like unimolecular reactions or what, and this macroscopic theories are ideas about how these discrete values end up just being spectral as about a continuum mechanics. So when we talk about the models of fluids, and then it's like, and besides that in electricity we have phase, and for example, and it's an extra property. It's got hidden variables in the theory, which otherwise would be built into the theory of fluids and vorticity, because it's the opposite that. It's not just like conductivity happens in the skin versus core effect. It's like, well, phase happens basically in terms of this alternating current. In terms of classically, it adds back down, but it's not the same. How the washing machine works. Usually by a wheel, for example, and not a big three-phase motor. Here for Einstein, though, in these discrete values, and what they mean is kind of like hydrogen spectroscopy or spectroscopy, and its ubiquitous success. That is like, well, yeah, we can characterize these substances by these spectral lines. The really spectral lines is ever a spectral analysis and finding an average over these continuous tone samples that results then just picking out the points that stick out. But it's subject to the 1/2 problem. Well, it's 1/2 problem. It's like, well, in a lot of these processes, we basically have this revitalization that's an unmodeled property and thus a hidden variable, and so empirically it's laid out this way, but it's a really, really sketchy mathematical contrivance, though it works. And so we try to leave it in only one place in the equation or wherever it needs to stitch together so the triangle rule holds everywhere else. And then between the triangle rule and this middle of nowhere type setup, then that's what you can find in most of these terms that have to do with discrete values and discretization in these continuous values in systems of continuous magnitudes. And it helps, hopefully it helps to explain why there are these things in the small that are in terms of these discrete values. Because given particular configurations of experiment, they do show up, and it's so modeled that because they're always exchanged in discrete values, that they keep that way. And that otherwise it's a model, it's a model of geometry is about points and lines, that there's no way to divide a line into points, and there's no way to make a point into a line except some non-standard way, and it's called line drawing. And it's pretty much similar with this particle and wave. And then there's also that really all our fields are not these classical fields, but all the potential fields that add up for the space-time, which is still kind of classical and real, although it's still also like a potential space because it just kind of falls in. That these systems of potential are really what we see when our classical view is of a particle in motion from instant to instant, obviously. You assign a value at any given instant what it has. But in this potential, it's this cumulative effect of all these other things. And so it just helps to explain a little bit the whole effort in quantization and discretization as a way to make discrete points on the line in terms of the points in a line, that there's even a difference between in a line, these points, and on a line, and you've tweezered or measured one of them. These are the kinds of things that get into the whole thing, that then having to deal with the quantities like so, and then like for Planck's length, and some people have that Planck's constant or length is, basically antithetical to orthonormal space, because if you had two Planck lengths at right angles to each other, their hypotenuse as a triangle would be an irrational number of Planck lengths. So it's just as bad for some people to say that Planck's length isn't vanishing than to say that geometry isn't Euclidean. And so this is one of the biggest stumbling blocks and the toughest things to figure out about physics, is that for the ubiquitous success after Rayleigh genes and after blackbody radiation and after the Millikan experiment in electron theory and the mass of an electron, that otherwise is really just a matter of current and density of 1 ampere, or in this kind of thing, ampere physics. That then is results for all these other matters, spectroscopy and measurement and this and that, monochromatic light as contrived, because light has variable and infinite frequency, while its velocity is constant, which is nice. That there's a difference between constants and utterly small constants, which are vanishing in infinitesimals. Because that matter of ratio, form, and proportion ends up being a matter for geometry, and then it gets into really why the geometry's models deconstruct into their elements and arrive at something true, and this halfway out of nowhere type thing, middle of nowhere. This reminds us of the fact that in acoustics, a series of discrete frequency values is coordinated to a linear partial differential equation if boundary values are given, namely the sinusoidal periodic solutions. In corresponding manner, Schrodinger set himself the task of coordinating a PDE for a scalar function psi to the given energy function E of QR, the momentum, PR, the position, where the QR and the time t are independent variables. Here, there's been a lot of reading of that from the path integral works, or Swanson's book, and Feynman, and also from that Mogan's nonlinear electromechanical effects and applications. Independent variables. In this, he succeeded for a complex function psi, and it's also framed in terms of all the Gaussian analysis and the Gaussian integral and the complex functions, which is a particular branch of a particular form of some particular preserved quantities in tensorial products that happen to be exhibited by the arithmetic of quantum numbers. That there's a lot attached to saying a complex function and its analysis than just the inputs and outputs are complex numbers. In fact, they're only real numbers, but the function's got to be defined on the complex plane about that part. In such a manner that the theoretical values of the energy h sigma as required by the statistical theory actually resulted in a satisfactory manner from the periodic solution of the equation. To be sure, it did not happen to be possible to associate a definite movement in the sense of mechanics of material points with a definite solution psi of QR, t of the Schrodinger equation. This means that the psi function does not determine at any rate exactly, emphasis the authors, Einstein's, the story of the q sub r as functions of the time t. According to Bohm, and Bohm wrote this restless universe, which is kind of his hypotheses of the thing. However, an interpretation of the physical meaning of the psi function was shown to be possible in the following manner. Psi, the square of the absolute value of the complex function psi, is the probability density of the point under consideration in the configuration space of the q sub r at the time t. It is therefore possible to characterize the content of the Schrodinger equation in a manner easy to be understood but not quite accurate as follows. It determines how the probability density of a statistical ensemble of systems varies in the configuration space with the time. Briefly, the Schrodinger equation determines the alteration of the function psi of the QR with the time. It's really kind of an optical effect and a flushing and a vorticial thing, and it has to do with this notions discussed previously about that the particle's extent is kind of like an advancing wave that it carries out. So there's either a linear impulse or like an expanding spherical impulse. And when that it reaches a point where it changes transition from its energy in one form to energy in another form, that's the detection. Because otherwise it's energy free in its medium. And then how that adds up in the media is its own kind of thing when it's continuous transition through media. And that basically defines when there's other interactions of other forms of energy or not. Because energy is conserved. And so here, this idea is that when the pilot wave or ghost wave, the pilot wave reaches the detector, that according to Heisenberg, it does not have a certain position of momentum, but when it hits it, it does. And then it will, and so it hits it as a circle does. And so one point circle reaches the detector, and at the back of the circle, it breaks there, and then it breaks everywhere else, and it coalesces, and it basically in zero time collapses to that point. It collapses to that point. The wave functions collapse. That it's a real instantaneous wave function collapse. So if you've heard of this quantum entanglement, it's like, well, the wave is over here, but when it collapsed, it actually drives the collapse of the detector at both points. Or it was one for the other, or that there were, two waves that otherwise would have joined or something like that. That it's contrived, basically, in terms of this energy in exchange. compared to that where it collapsed and how it arrived in terms of its wiggly motion as how it's diffracted randomly by a one of the slits in the experiment, because the wave action according to the frequency and variability of light can be adjusted, that according to the diffraction according to that grating can be adjusted, and it can be seen how it adds up then after it goes. So it looks stochastically, it's because where the real wave function collapse starts on that circle that's the wave outside could be anywhere, and so it's essentially where it is though is spinning around so rapidly that it's trying to flip a coin and catch it in your hand, and knowing just from the frequency and hearing how many resonances that made, what side it landed on. It's possible. You can train yourself to flip a coin and catch it in your hand and without looking and guess reliably, much more than 50%, which side it lands on. So the idea for this, that's not necessarily so for this probabilistically modeled particle that has a real wave function collapse, that it has a spin that's arbitrarily high. That the quantum numbers of spin are basically just qualitative. Like spin 1, spin 2, these kinds of particles, they kind of spin, to infinity, 1 infinity, with respect to these other transitions. That's why it ends up acting over time as modeled by the behavior, because it's just a lot of large numbers that, though it can be deterministic in a real wave function collapse, it just falls down from that. Again, the idea is to keep infinity out of physics, and so a probabilistic interpretation, quantum mechanics, works great for that. There's nothing wrong with it. It's exactly so explained by the same thing. But these days it's understood that the wave function is a real thing, and so Bohm and de Broglie have gotten a lot of credit where before they were paint canned. And then Born kind of just says, hey, look, I found something that adds up for you, and Feynman's going to really appreciate this and use it for all of his work and get really famous. It's like, sure, yeah, all right. It is therefore possible to characterize the content of the Schroedinger equation in a manner easy to be understood but not quite accurate as follows. It determines how the probability density of a statistical ensemble of systems varies in the configuration space with the time. Briefly, the Schroedinger equation determines the alteration of the function psi of the q sub r with the time. It must be mentioned that the result of this theory contains as limiting values the result of the particle mechanics that the wavelength encountered during the solution of the Schroedinger problem is everywhere so small that the potential energy varies by a practically infinitely small amount for a change of one wavelength in the configuration space. Under these conditions, the following can in fact be shown. We choose a region, big G sub 0, in the configuration space, which, although large in every dimension in relation to the wavelength, is small in relation to the practical dimensions of the configuration space. Under these conditions, it is possible to choose a function of psi for an initial time t sub 0 in such a manner that it vanishes outside of the region G sub 0. The eigenfunctions and the eigenmodes of the eigenproblem of the usual framing of the Schroedinger equation solutions in the linear, having all these higher order solutions with not real values, is kind of a thing. That doesn't necessarily mean they don't have a physical attachment, but it doesn't necessarily mean they do. And here, if it's about gravitational lensing, I'm a little curious about it, because I think that's kind of defined by Fresnel, but it might work up about the same. It behaves according to the Schroedinger equation in such a manner that it retains this property approximately at least also for a later time, but with region G sub 0 having passed at the time t into another region G. In this manner, one can, with a certain degree of approximation, speak of the motion of the region G as a whole, and one can approximate this motion by the motion of a point in the configuration space. This motion then coincides with the motion which is required by the equations of classical mechanics. At usual scales, everything is a particle and everything is a wave, but at usual scales, it's modeled as a particle, and it's classical. Experiments on interference made with particle rays have given a brilliant proof that the wave character of phenomena of motion as assumed by the theory does really correspond to the facts. In addition to this, the theory succeeded easily in demonstrating the statistical laws, the transition of a system from one quantum condition to another under the action of external forces, which from the standpoint of classical mechanics appears as a miracle. The external forces were here represented by small additions of the potential energy as functions of the time. Here he might be describing some apocryphal experiments which he hasn't detailed, but again, that's part of this. This is a theory of some potentials. So there is non-locality there, and there is the instantaneousness of certain contrived relations. And so that would be okay, and explained. The external forces were here represented by small additions of the potential energy as functions of the time. Now, while in classical mechanics, such additions can produce only correspondingly small alterations of the system. In the quantum mechanics, they produce alterations of any magnitude, however large, but with correspondingly small probability, a consequence in perfect harmony with experience. Even an understanding of the laws of radioactive decomposition, at least in their broad lines, was provided by the theory. This again is about the success of quantum mechanics. Sometimes people say, quantum mechanics is never wrong. If you got the wrong answer, you're doing it wrong. And figure it out. Probably never before has a theory been evolved which has given a key to the interpretation and calculation of such a heterogeneous group of phenomena of experience as has the quantum theory. In spite of this, however, I believe that the theory is apt to beguile us into error in our search for a uniform basis for physics, because in my belief, Einstein's belief, it is an incomplete representation of real things, although it is the only one which can be built out of the fundamental concepts of force and material points, quantum corrections to classical mechanics. The incompleteness of the representation is the outcome of the statistical nature, incompleteness of the laws. I'll now justify this opinion. Now for this, you can read much of what I just said about it. I ask first, how far does the psi function describe a real condition of a mechanical system? Let us assume that the psi sub r to be the periodic solutions put in the order of increasing energy values of the Schrodinger equation. Usually the eigenvalue problem so associated. I shall leave open for the time being the question as to how far the individual psi sub r are complete descriptions of physical conditions. The system is first in the condition psi sub 1 of lowest energy, energy 1. Then during a finite time, a small disturbing force acts upon the system. At a later instant, one attains then from the Schrodinger equation a psi function in the form psi equals sum of the c sub r psi sub r, where the c sub r are complex constants. If the psi sub r are normalized, then the absolute value of, or magnitude, the length of c sub 1 is nearly equal to 1. C sub 2, etc. is small compared with 1. Here, this is that this system has a linear set of solutions, which is not necessarily so. But one may now ask, does psi describe a real condition of the system? If the answer is yes, then we can hardly do otherwise than ascribe to this condition a definite energy E, and in particular such an energy as exceeds E1 by a small amount, in any case E1 less than E2. Such an assumption is, however, at variance with the experiments on electron impact, such as have been made by J. Franck, F-R-A-N-C-K, and G. Hertz, H-E-R-T-Z, if, in addition to this, one accepts Millikan's demonstration of the discrete nature of electricity. So now I'll be curious about Franck and Hertz, and Hertz is familiar as cycles per second, or, Hertz is 1 over time, 1 over second. And so I'm interested in this inverse Hertz and about the recitative and oscillative, which can be real and still evaluate that otherwise that these discrete values have ordering maintained. And kind of like when there was talk about complementary sign, like sine is a periodic function. You can't tell its ordering. Given any two particular values, they in increasing x, they might or might not have ordering. But if you divide that by x over time, that goes to 0 still. Whether or not that's kind of relevant, this kind of thing in terms of the bounds of otherwise the energy. In terms of aggregate terms, area terms, areal terms. As a matter of fact, these experiments lead to the conclusion that energy values of a state lying between the quantum values do not exist. And so here it seems he's taking a particular approach with a particular setup, and there's lots to be read in the linear and nonlinear and these eigenvalue, eigenmode problems and their decompositions and the singularities involved in this kind of stuff. But otherwise, this seems like a fair argument, and it's also kind of a defense of the whole discretization, quantumization, and quantization effort, because it ends up providing real values for these things where they can exist. And then hopefully he's going to give us an explanation of something that would be an anomaly and how they solve it, and what's the convention to solve this kind of anomaly. But represents rather a statistical description. It seems to be clear, therefore, that the Born statistical interpretation of the quantum theory is the only possible one. It seems to be clear. The psi function does not in any way describe a condition which could be that of a single system. It relates rather to many systems, to an ensemble of systems, in the sense of statistical mechanics. If, except for certain special cases, the psi function furnishes only statistical data concerning measurable magnitudes, the reason lies not only in the fact that the operation of measuring introduces unknown elements which can be grasped only statistically, but because of the very fact that the psi function does not in any sense describe the condition of one single system. Here it's a system of potentials, and in terms of any hidden variables, it's a fair collection of what is a distribution that has, according to the distribution of these elements, usually linearly, and what ends up being the expected values of samples of it. And now there's a footnote, and it was on the to ascribe, otherwise than ascribe. Because according to a well-established consequence of the relativity theory, the energy of a complete system at rest is equal to its inertia as a whole. This, however, must have a well-defined value. So for this, that's here for that rest exchange momentum theory, why that can kind of come and go, but it's not at rest. It's dynamics, but otherwise it's fine, it's at rest. The Schrodinger equation determines the time variations, which are experienced by the ensemble of systems which may exist with or without external action on the single system. Such an interpretation eliminates also the paradox recently demonstrated by myself and two collaborators, and which relates to the following problem. Consider a mechanical system constituted of two partial systems A and B which have interaction with each other only during limited time. Let the psi function before their interaction be given. Then the Schrodinger equation will furnish the psi function after the interaction has taken place. Let us now determine the physical condition of the partial system A as completely as possible by measurements. Then the quantum mechanics allows us to determine the psi function of the partial system B from the measurements made from the psi function of the total system. Energy input. This determinant, however, gives a result which depends on which of the determining magnitudes specifying the condition of A has been measured, for instance, coordinates or momenta, according to Heisenberg picture. Since there can be only one physical condition of B after the interaction which can be reasonably not be considered as dependent on the particular measurement we perform on the system A separate from B, it may be concluded that the psi function is not unambiguously coordinated with the physical condition. Well, it's two measurements, and variations multiply, discrepancies multiply. This coordination of several psi functions with the same physical condition of system B shows again that the psi function cannot be interpreted as a complete description of the physical condition of a unit system. It's got two psi functions. Here also the coordination of the psi function to an ensemble of systems eliminates every difficulty. And that's when there's one, because I think that he's just describing that the observation and sampling measurement and effects. He's like, does it really mean that when you measure something that it actually affects it? And like the watch quantum teapot never boils? It's kind of like, yeah, because it actually causes an exchange of energy somehow. It actually causes, dipping the meter stick into the stream does actually affect it somehow. And that might not that make zero effect if it's like this probe is infinitesimally small. But when it's going around 1,000,000,000 times a second, or however fast you want to model spin, as infinitely fast spin, the isinglass or whatever you want to call it, about that all it has to do is barely deflect that at all, and you would end up totally different conditions on the outset. Doesn't it? It's only got in so much inexactness as that it must be modeled probabilistically by normal means, that otherwise whether or not it can be affected determining the establishment of infinite spin is to be modeled in systems that basically have of propellers and turbidity and vorticity and the helical and cavitation. So anyways, that's the description of the thing, and I guess that's where I'll leave it for the moment. And we're up to page 91 of Out of My Later Years, and the page begins, the fact that quantum mechanics affords in such a simple manner statements concerning apparently discontinuous transitions from one total condition to another without actually giving a representation of the specific process. This fact is connected with another, namely the fact that the theory in reality does not operate with a single system, but with a totality of systems. All right, yeah, I agree with that. Hey, have a great day. Good luck.